Hello. What we're going to talk about today is risk management. A fair amount of the material I'm going to pull from is from a book called Computer-Related Risks by P.G. Newman. And so I won't directly quote all of it, but that's a lot of where the source of it comes from. So we're at the point of the time now where as you're working on your projects in the course, it's time to actually start thinking about this notion of risk. We haven't talked about it yet, but before you go much further on the project, it's something the team needs to think about. And it's something that the team needs to decide upon what are the risks and how to mitigate them. So today we're going to be talking about what risks are, some of the natures of their sources, an understanding of all of this, because it's very important to every single software project, because all software has risks. Absolutely, all of it does, and it's beholden upon the engineers building and designing the software to actually take the time, identify what the risks are, and decide what's necessary to mitigate against all the unacceptable risks. So let's start with a definition from NIST, their publication 830. This is the National Institute of Standards and Technology in the United States. And this is they're a bit focused in this document a bit more on security, which is a major portion of risk management. But nevertheless, this definition, I really like it as a really good one. So risk is a function of the likelihood of a given threat sources exercising a potential vulnerability. Boy, I've got to work on my pronunciation. And the resulting impact of that adverse event on the organization. And so the really big things here, of course, is what we're talking about is what is a risk? Basically, it's how likely is something bad going to happen to a person or an organization or society, given that basically there's something potentially wrong with our system that we've built, and it actually being somehow exercised so that wrongness actually comes to be. And so this puts it all together, and it gives us a way to start to think about the notion of risk in what we build. So let's look at this a little bit more detail. So again, we're going to work with a little bit of defining some things. So vulnerability. So a vulnerability this is a weakness in the system that we've created. And I think one thing that's important to I'll just mention now is a system is not just the software. It's the total, it's use embedded within organizations, with the users, with the hardware, the world. So this complete system of a whole bunch of things interacting with the software. So it's not inherent to the software alone. Software is part of an overall system. So it's a weakness in the system that may result in harm. All right, and so you could think of it, if you want, as a quick way to remember what a vulnerability is. It's like a chink in the armor. So you've got this nice suit of armor, but there is a problem with it somewhere. And normally it's not an issue. But let's say, I was to be attacked by someone with a sword and they find my chink in my armor, then that vulnerability becomes a real problem. All right, so what's a threat? Well, a threat is something that could take advantage So this would be my attacker with the sword. or accidentally trigger a vulnerability. And so basically we have sort of an intentional notion of taking advantage of vulnerabilities and unintentional ones. These are unintentional ones are terribly common. And we often see those with the human-computer interaction and the interfaces that we build into the system. The people using them expose the flaws that we have accidentally. They don't actually try to do something bad. So if you wanted to, we could sort of see risk then as being sort of the probability that a threat exercises. So this could be intentional or unintentional. So the exercise basically means they cause the vulnerability to become a problem, multiplied by whatever the harm or impact is. So if the harm and impact is really small, so even if the probability is really high, the risk is low. Likewise, as the harm and impact become serious, really low probabilities might make us not as concerned about it from a risk standpoint. Except I'm going to skip ahead here and say, you know what, if this harm and impact has to do with human life, loss of life, any non-zero probability here is something to be very concerned about. Okay, because you can think about loss of life as practically, it's like infinity. It's so horrible that any probability here is something that turns into a potentially unacceptable risk. So anytime that we think about human loss of life, that's when we need to actually be in a completely different state of mind. So let's give you a thought about this. I mean, it's an example, not a thought. And again, we're going to start to talk about dramatic examples here with loss of life. So a warning to you about that. But it's important that we kind of have these examples because they give us reason why risk mitigation is such an important thing. So identifying the risks and preventing them. So I want to start with a non-software example for you. Okay, this comes about, this is from a story in a newspaper article in 1993. And it involved a 12-day-old baby. And the baby was in the hospital and was needing to be monitored still. Hadn't gone home yet. And so they put a heart rate monitor on the child. And so, you put an electrode here and an electrode here. It's simple. It's like if you've ever seen things for sport and monitoring your heart rate. It doesn't take much. It just needs to be able to measure the electrical impulses that your heart makes and stuff. And so that comes off with a cord, and that cord then is to be plugged into the heart rate monitor. Right? Simple enough. And that way the nurses can monitor the baby and know that everything is okay with the baby. We always see these in television, beep, beep, beep. This is nothing unusual. Well, unfortunately, in the worst sense, unfortunately, the plug for the heart rate monitor had two leads, two pieces of metal basically sticking out of it, and it just so happens that they were spaced in size such that they would also fit not just into the heart rate monitor, but they could also fit into a standard 110 volt outlet. And this is absolutely what happened. In the confusion and hustle and bustle of the hospital environment, a nurse plugged the heart rate monitor into the 110 volt outlet. It fit, no problems. And unfortunately, then 110 volts went across the child's chest and killed the child. So if we think about that, what was the vulnerability here in this tragic accident? Well, basically the fact that the plug could also go into a dangerous outlet, which would actually be available because of the way that instruments and power is made available in hospitals. Okay. This is not a problem that you would probably have at home. You probably wouldn't have all the power next to your child and be likely to make it, but in these big stands and stuff, absolutely. And so that was the vulnerability. And then what was the threat? Well, the threat was accidental human error under stress and time. And well, we put that together. What was the probability of happening? Well, this was an article from 1993, and this design problem, and it was a design problem, was first detected in 1985 by the U.S. Food and Drug Administration, which issued a nationwide warning after the electrocutions of several babies. So not just one mistake, but this happened many times. So the probability is not sort of, oh, there's no way this would happen. No, it was up there. And the consequence then was horrible. We have loss of life. Just you go, okay, well, that's not software. We're supposed to be talking about software here. Well, perhaps the most classic example in software is the Therac 25. Okay, so the Therac 25, and you can read about this online. In fact, maybe right now you go do a quick Google search. This is a computer-based electron accelerator, or was one. It's no longer in use, is my understanding, for radiation therapy. And the problem was a combination of the software and hardware. So again, it's a total system issue. It's not just software, but software is part of the problem. Basically, the flaws allowed an operator who uses it. So this is you have cancer or something, and you need to go in and get radiation therapy. And so the operator puts in what is the treatment that you're going to need into the system. So it allowed an operator to accidentally overdose patients. All right, and so they know that there are 3 dead from these mistakes and 3 people injured. So here they're going to aiming to be saved, but instead, through the combination of how the operator, it was something as simple as this, where they typed in a parameter and said, oh no, that's wrong, and they quickly changed it. And the way the software worked in the editing, it and the interactions with the hardware then put the machine into a state where it didn't actually control and reduce the amount of radiation, but would release a full blast of it. And so, yeah, terribly, the patients would recall they did basically like a huge flash of light, burning sensations, and then then they would die a short time afterwards from a radiation overdose. Absolutely horrible. And in the investigation of these accidents, it took a lot of work actually to find the issues and the problems, because they repeatedly would go back and they test the software, and the software, we can't find any mistakes in it. So they'd blame the operators. They don't know what the operator did, but something must have gone wrong. But the reality is they were actually able to find that there were flaws in how the software worked, and it was possible for accidental, just through the normal usage, without any warnings at all. The hardware safeguards would be disabled or not in place, and loss of life. And so this was over 30 years ago. But what's dismaying about this, in 2010, the New York Times ran a report on similar problems with other manufacturers of radiation equipment, and this article doesn't even mention Theric 25. Enough time had gone by that journalists investigating these phenomena had no idea that it had actually happened before. And so they were reporting again that with these types of instruments and equipment in hospitals, that patients were getting overdoses, and it was the same sort of problems with the way that the software interacted with the hardware. So we build systems as engineers, and we need to be mindful of their use and their deployment in society. All right, we need to be able to identify these risks and then to be able to mitigate against them. So, by the way, in that computer-related risks book by Newman, it's this thick, filled with summary after summary after summary after summary of mistakes of actual deployed systems that have led either to to loss of life or other things. And studying these sorts of mistakes is actually very, very useful, and it helps us understand the type of mistakes that people make. And so we could have an entire course on this, but what I'm going to do here is try to give you a brief summary, an introduction to this, to be able to help you to get to think about these sorts of things. So what are the common threats that we see with software systems? Well, first is natural or nature, okay? So, and again, it's just even putting these down and writing them down makes you go, well, maybe I've never even thought about that. And that's part of the thing, is we need to think about these things. And so, lightning. When I was an undergraduate, I worked in a physics laboratory. I still remember finding out that, yes, in this physics laboratory, it would get data from a telescope down in Arizona, and that's on top of a mountain. And one time, it got struck with lightning, and apparently the lightning went in and actually melted and fused components inside the computer. And I believe there was some data loss, but there certainly was always a process of having backups of everything, and so the loss was actually minimal. But these things happen. If there hadn't been backups being made, that would have been a significant loss to the system. You can have earthquakes, floods. I just think about New York City, and several years ago I remember having management engineering students there on co-op, and they got embroiled in the hurricane that came in and caused all sorts of flooding, and the people had computers and they got flooded. You don't think about New York City as a place of flooding, but it did happen. Okay, and this is one of the things is we often underestimate the chance that something bad's going to happen. Just recently, Texas, all right, got really cold, horrible consequences for the people there, a significant loss of life as a result of this, and all sorts of destruction of property. And I'm sure it impacted systems where software were involved as well. And if they hadn't been planning on that, those disruptions, there could be all sorts of bad outcomes. Electromagnetic radiation, this can be caused by other equipment around. Cosmic radiation, we're always having charged particles passing through us. Those charged particles, when they pass through computer systems, they can cause a bit to be changed from a 1 to a 0 or a 0 to a 1. These sorts of mistakes then can propagate within the software or cause other sorts of flaws. It's something to be considered about. Often the servers that are used in data centers have what are known as error correcting memory. They use error correcting codes, but most of your regular desktop and personal computers do not. And so imagine if you build a system out of a regular set of desktop equipment, you could be subject to problems caused by cosmic radiation. And if software wasn't designed to handle those or the failures in the computers caused by them over time, you could actually have some serious flaw in your system. Other things in nature, animals tend to get into things. It's not unusual for an animal to cause a power outage somewhere and so forth and so on. There can be infrastructural. So again, big one here is loss of power. What is going to happen to the computer system when it loses power? If it's not on a battery backup, and let's say you're in the middle of, it's some sort of transaction maybe, it's working for a bank and you're saying that this account is going to get money and I'm going to take it out of this account, but you haven't finished that transaction yet, you lose power. What is going to be the nature of that? Are you going to have accidentally taken money out but not put it back into another account and lost the money? Are you going to have put it into the account and not taken it out of the other one and thus the bank loses money? I mean, so how is the system designed to handle that? Because even if you had a battery backup, eventually that battery probably is going to die. So do you have a generator? Well, so forth and so on. But what if you do lose power? What if there's some failure? Is the system designed to actually handle that appropriately? We can have hardware malfunctions. And, simple as hard disk drives actually dying or a power supply failing to continue to work. The physical nature of computer systems, they do wear out. They do age. And they can have hardware malfunctions. We can have communication failures. We often think of our main computers all nicely connected, and there shouldn't be a problem. But again, what if in the midst of doing something that connection is actually broken? This is either caused by loss of power somewhere else, someone accidentally unplugging something, someone accidentally cutting a cable outside. All sorts of things can happen. How does the computer system deal with that? What's potential issues? Now, you might be like, oh, come on, do I need to worry about this stuff? And the answer is, you need to go through it and think about, for the system that you're building, what is the potential harm that could occur. What vulnerabilities do you have? And what's the likelihood and what's the harm potential? And then decide whether those are unacceptable risks or not. So other threats, big one, really human. So there's unintentional, and we really have to think hard about this one. So you can have simple, for example, data entry mistakes. So I just type in the wrong stuff. I put in too large of a value, and now the system does something aberrant. Imagine you're controlling a robot arm in a factory. You put in the wrong values. There's not proper hardware constraints or safety zone in something, and before you know it, the robot arm moves and crushes someone, injures them. But it's just a simple mistake. So this is unintentional, but you have to watch out for that. And it could also, doesn't have to always be loss of life. There's all sorts of other things. But there's all sorts of human-computer interaction issues. Several years ago, the state of Hawaii was running a test of sort of their emergency announced broadcast system. And it wasn't clear in the user interface, and they accidentally broadcast a message during the test to everyone in the state of Hawaii via their mobile phones that there was an incoming missile attack. It caused great distress. I think it might have caused some other bad outcomes as well. But it was, if you go look at the images, it's really clear that it was a pretty easy mistake to make based upon the way they designed the system. And so, and in fact, it was actually hard for them to know that they'd made this mistake and to actually, once they'd made it to actually rectify the mistake. So there's a whole bunch of stuff there that is unintentional done by people, and human-computer interaction is a really critical thing that we have to look at. But then, as well, we have intentional attacks. And so you, of course, have the classic, the hacker, the person who's trying to break into the system and steal data, manipulate bank accounts, all sorts of things, steal your identities, horrible stuff there. So we have a whole sorts of things with security purposeful, but as well, you could have an upset employee who internally decides to sabotage things. Is the system designed to manage against that? Or perhaps more likely than a upset employee is an unethical employee. Okay, and so consider, let's say, for example, you've built an online email system, and let's say when you store the email messages into the database, you just store them in plain text. Okay? So, for any engineer working on that system who does a select star or whatever, they can read everyone's email. Well, if you're unethical, you can go in there and purposely read your boss's email. Read your girlfriend's email. There's all sorts of cases of people with access to sensitive data sources using them for unethical purposes. And for example, like the email situation, it should actually be, there should be controls, restrictions on who has access to that. And likely as well, the data itself should actually be stored, encrypted in the database, such that it's extremely difficult or impossible for, even if someone was to steal that data, for them to be able to find out and access it. And so if the system isn't, if you don't think about these risks, that potential, you won't have mitigated them. And the next thing you know, yes, you do have some national, broadcast story about the problem that has happened as your system has been hacked or an employee has made a mistake, left a laptop somewhere, so forth and so on. All right. So what are sort of the sources of these vulnerabilities? Well, one of the really major ones are actually incomplete or wrong requirements. Now, we're doing Agile in this course, and we're taking an approach to requirements that basically we're working with the client and we're trying to figure things out and trying to get things to work. And this is a great technique for the type of software that we're building. We're building, systems that are designed to help people in simple ways, or data processing. They're in many cases the chance for impact and harm often is we're keeping them fairly low. But there's a lot of systems out there in the world where that's not the case, and you need a stronger set of effort towards determining the requirements. An example of this comes from the battleship or the ship, the Sheffield, during the Falklands War. And this was a ship that was sunk by a missile. Now, the Sheffield had anti-missile defenses, but in the requirements, they didn't catch the issue that the frequencies, the radio frequencies that the anti-missile defenses would operate on were chosen to be the same as communication channels that the vessel needed to communicate back to headquarters. And so at the time of the attack, they had disabled or were, unfortunately, the anti-missile functionality was jammed because of the communication equipment. So they might have very well disabled their protective device because it had interfered. This is a requirements problem. They didn't identify at the time, which they should have, which are what are all the radio frequencies and channels being used by this battleship. All right. Unfortunately, yes, the ship sunk. And they should have gotten that right. System design flaws. So you design the system in a bad way. So you could envision that maybe this is you used an incorrect algorithm. So you didn't code the algorithm wrong. There's not a bug there, but you used the wrong algorithm, and that would be a design flaw. Okay. Of course, you could have bugs in the system. That's pretty obvious. And then as well, you can often have these false assumptions about the world or the usage of your software. So this latter one is often, oh, no one would ever type that in. Who would ever do that? Well, trust me. Don't make assumptions about the way it's going to be used, or, well, of course it's going to be used correctly. My favorite example of this that's not software is with all of our roundabouts. It's pretty clear, if you dig into it, that the traffic engineers are, well, if everyone would just learn all the proper rules, the roundabouts would work great. Well, people don't. And they're confusing and they're hard, and we have accidents and we have loss. We have pedestrians frequently getting hit. So that's a terrible design flaw based upon we're going to blame people rather than blame the design of the system. All right. So there's a really nice article entitled "The Therac 25, 30 years later. And this is by Nancy Leveson. And she did the primary analysis. It took several years of the original accidents with the Therac 25. And so she looks at this 30 years after it happened. And unfortunately, she notes that we still face a lot of these problems in our software systems. And so this is a summary of that article. A lot of times we have an overconfidence in software. And what she means by that is, we think software doesn't, break or wear out like mechanical devices do. And the big thing here is that this is wrong. Okay, so the idea was, you build a mechanical system and you understand that mechanical things wear out or they can actually physically break. So you actually you'll build redundancy so you don't have single points of failure. That's like a simple design principle. Well, I don't want a single point of failure, so I'm going to have some redundancy in the system. But now people with software, they're like, well, if the software works, it doesn't actually ever break. It's not like it wears out. It's just software. So people then don't think about software in terms of breaking. But time and time again, we find that our software, based upon it's embedded in this overall context of a larger system with people and hardware and all of these things, we can have flaws that we are not aware of that effectively then it breaks. And we fail often to actually have in the redundancy that we would have had with mechanical systems when we've replaced them with software systems. And instead, so people are overconfident in them, and they shouldn't be. You should expect your software components to have flaws and problems in them and to be prepared for that. Likewise, confusing reliability with safety. So in other words, this gets again at the notion where people are like, it's bug free. I'm convinced there's not a bug in it. It's highly reliable. Well, that doesn't mean it's safe. Okay. And again, the reason is, this comes back to before, but most software accidents that have been recorded are requirements problems. And in fact, Nancy Leveson, she's actually in aeronautics. And so she looks at all sorts of issues with planes and software. And so this is certainly something that we don't want to have. And so what this really tells us is that when we're working on software, it's very important to identify safety critical requirements. So a critical requirement is a requirement that is related to human loss of life, okay? And so you have to identify these requirements that are related to these things. And then you have to build in the safety. It's not about making it just bug-free is important, but it has to be designed with safety in mind. And so you need to be identifying these requirements. Very critical. So another thing that is identified in that article that we have problems with software systems is lack of defensive design. So people write code often with assumptions being made. So I assume the data I get in will be of this sort. Well, what happens when the data is not of that sort? You should check, for example, the data that comes in. And if it's not within the range that you were designed to handle, you should reject it and safely exit rather than cause harm or make mistakes or errors. So that's just a really simple example, but you need to think about, even at the smallest unit of your software, well, wait a minute, what could go wrong? What assumptions does my software really have in it, the code that I'm writing? All right, well, if those assumptions are violated, I need not to actually proceed. I need to report that as an issue so it can be handled appropriately. So there's all sorts of stuff there. One of the other things is we don't actually know what the probability of a threat exercising a vulnerability is. You could make guesses, but that's all they are. They're estimates. So we don't really know this. And so basically this means that we have to design for the worst case. Especially, again, if we're dealing with a critical requirement, a safety critical issue, because we don't know what this probability is. Unless it's actually truly zero, there is still a chance, and then we should be designing for the worst case. Too often people apparently will do sort of an analysis of the risks and determine, oh, that probability is really, really low. Time and time again, it's turned out that even very low probabilities actually aren't that low. We'd misestimate them. Very frequently, we often blame the users. And so rather than our designs, oh, it's the user's fault, it's the user's fault. No, the reality is it's the design fault. Don't blame the users for misuse. You have to actually work with it so that the users can actually not make mistakes. So for example, you should design things basically so that if you're gonna, if there's safe things in a system, yes, they should be easy to do. Wonderful, make it simple. That's great, it's safe. Now, if there's something that's unsafe potentially in a system, it should be hard to do. So for example, unsafe thing would be to disable an alarm. If the temperature of the reactor is too high, I get this warning. I want to turn off the siren and the flashing lights. That should be really, really, really hard or impossible for an operator to do in the system. Same goes for all sorts of things. If you could put the system into an unstate safe, it should be something that requires a lot of work to do. Again, safe things, make it wonderful, make it fun and easy to do. But if you could put a system in an unsafe state, it should be a lot of work to have that happen. All right. I will say that, so another point that she makes in this article is that our software engineering methods, for example, simple websites, that sort of things that we've been building in our course are not suitable. Productivity systems and so forth and so on are not suitable for safety critical software. So don't think because you've learned how to program and we've talked a little bit about this that you're ready to go work on safety critical systems. We haven't taught you about how to do this, and these methods that we're teaching you are great for building productivity apps and other sort of basic information systems, but safety critical software is a whole separate matter. All right. So let's talk then about, so now we've talked about vulnerabilities, we've talked about threats, we've talked about sort of the common problems that we see in software and our design there. What really, let's wrap this up here with talking about the bad things that can happen, the effects. So this is, harm. And so we can have things that affect life or our property or some sort of nuisance. So what are the bad effects that we could have? Well, at the top of the list, we can have death. There could be risk to life, not actual immediate death, I guess. Resource loss. So these are things like, we lose the data. We didn't have a backup, we lost the data. Or the data in the middle of a power outage transaction. We could lose time to recreate the work that's in a system when we have a failure. We can have all sorts of money loss as well, all sorts of other things possible. And and then there's other risks. And these might be very small, such as your Facebook status is wrong or something. So I got a bug. It might be embarrassing to your status incorrectly says something about, your significant other or whatever, but it's probably not going to result in anything worse. And so, of course, this is bad. That I think what the important message out of this that we really want to communicate and talk about here is what should a management engineer be doing? What should you be doing on your project? Well, what you should always be doing is, again, all right, so what to do? Well, for all sources of risk, you really need to ask yourself, what will happen if? So what will happen if the user types in the wrong data? What will happen if we do have a computer failure? What will happen if so forth and so on? What will happen if our authentication and authorization system has a bug and allows people to access data they shouldn't be allowed to access? What are all those sorts of possible things? And so you have to actively work to think about the nature of your system, the data it has, the usage with the people, who might want to do harm, who might want to break things, all that sort of stuff. Go through all of it, identify the risks. So that's the first thing, is that this is basically identify your risks. And then the greater the risk, or potential harm. Quite simply, the more care and time must be taken to mitigate the risk. We want the risk to become such that everything is acceptable. Now, with this in mind, again, I want to also stress that as an engineer, it's very important to know your limits as an engineer. Okay. For example, again, you are not trained for safety critical software. And so if you were to ever be in a circumstance where you were working on something where there was risk of life, you should know that probably you need to seek additional help and expertise and so forth and so on. Can't die, oh, I've had a little bit of education in software, proceed on those sorts of things as an engineer. You have to seek the proper training and expertise to actually deal with those sort of systems. Besides just the basic ethics of it, there are also laws regarding it. And we don't want you to run into those. And so this, identify the risks, and then you have to actually work to mitigate again. And so in your projects this term, yeah, you want to actually have gone to the effort to identify what are the potential things, what are the potential risks, what have you actually done to mitigate against those risks, or at a minimum, made those risks aware to the client so that the client can make proper decisions about the reasonableness of deploying the software. But in general, you shouldn't really leave it to the client. You shouldn't give the client something dangerous. They should be actually mitigated against. So you have to do risk identification so that you can get to the mitigation, so you can manage your risks. Now, I know that a lot of you are probably also saying, oh, come on, does this have anything really to do with management engineering and the types of projects that we're going to work on? And the answer is absolutely. And I'll cover those in examples in another video.